So, dear learners, next session we are going to discuss about supercomputing quantum processor. Just is it isn't going to be a hardware information, how it is going to be utilized inside the quantum simulators. We are going to see that in this session. So, this session outcomes reveal introduction, history, quantum computer and qubits, QC performance, technologies for implementing QC, superconducting qubits, qubit control using quantum logic gates, superconducting quantum circuit basics, quantum processor. So introduction, this particular session is going to reveal the world's most difficult challenges. There are several models of quantum computing, which includes quantum circuit model, quantum Turing machine, adiabatic quantum computer. The most widely used model is the quantum circuits out of these. So this is a philosophical evolution uh, depiction. So which states different philosophers or inventors who has proposed some sort of ideas which has been integrated in the quantum simulator environment in the quantum computing world. First is 1982, Richard Feynman proposed the idea of creating machines based on the laws of quantum mechanics instead of the laws of classical physics. So in 1985, David Deutsch developed the quantum Turing machine, showing that quantum circuits are universal. In 1994, Peter Shor produced a quantum algorithm to factor every large numbers in polynomial time. In 97, Lou Gower is another philosopher or inventor, develops a quantum search algorithm with complexity of O square root n. What is quantum computer and qubit? So we have already seen in previous sessions. So we are going to see an output in the console window, which is going to have small sort of confusion to the viewer that it can exist in a state either in terms of 0 or either in terms of 1 simultaneously. So from the reader's perspective, it will reflect the answer either in terms of 1 or 0, or the state is called to be the Bell state, where top will reflect 0 value and bottom will reflect the 1 value. Make use of two key principles of quantum physics, superposition and entanglement. Qubit can be either 0 or 1, 0 and 1 at the same time. Quantum computer performance offers vast parallelism. The exponential increase in power. A 100 qubit quantum computer is more powerful than a supercomputer. Number of qubits, classical possibilities and power. So 0 or 1, 0 0, 0 1, 1 0, 1 1. So whenever you are going to hold 3, n is going to hold a value in terms of 3, and you are going to held up with the value in terms of 8, where you are held up with 000, 001 and 010, 011, 100, 101, 110, 111. Technologies for implementing quantum computing. There are 7 core qubit technologies for quantum computing. First one is supercomputing qubits. Second is semiconductor quantum dots. Third is trapped ion. 4 is photonic qubits. 5 is defect-based qubits. NP-hard problem. It will be called as an NP-hard problem, which is more related to diamond. Topological nanowire qubits. Majorana qubits. It will be reflected as Majorana qubits. 7 is called to be as a nuclear magnetic resonator. So the waves will be passed as if the waves will be passed in the diamonds. You can't able to identify how the qubit is going to throw the flavor of composition in each and every side of a sector. So photons is going to pass through the qubits, where the photons can't be holded by anything, and it is going to reflect some sort of thing called to be as a newer answer. Superconducting qubits. Superconducting qubits are solid-state electrical circuits. Compared with the qubits based on the other computing systems such as trapped ions, nuclear magnetic resonance, linear optical systems, etc. Supercomputing qubits have the following advantages: high designability, scalability, ease to couple, ease to control. Supercomputing qubit archetypes. Supercomputing qubits generally consist of supercomputing electrodes or islands that are interconnected by Josephson junctions. According to different degrees of freedom, superconducting qubits are mainly divided into three categories: charge qubits, flux qubits, phase qubits. Based on the three superconducting qubit archetypes, many new types of superconducting qubits are derived, such as transmon type qubit, She-shunt flux qubit, fluxonium, uh, and 0 to alpha qubit, where every material is getting discerned and differentiated. Transmon qubit. The transmon is a supercomputing qubit. Transmon type qubit are transmon, xmon, gmon, 3D transmon, etc., which will be present or solidar inside an PCB board. The most popular superconducting qubit is called to be as an transmon qubit, where you are going to have the electrical charges which is going to pass the photons. Consists of two islands interconnected by one junction. The induction is provided by Josephson junction. Qubits lifetime. By improving the structure and parameters of supercomputing qubits as well as the preparation techniques and materials, the lifetime of the superconducting qubits has been greatly enhanced. This table summarizes the development in the lifetime of qubits over the past decade. The development in the lifetime of qubits in recent years. Each data uses the highest value reported in the literature of the current year, and it is not recorded if it is smaller than in previous year. That is the value. So this table reflects the lifetime of the qubits, either in transmon, either in the flavor of xmon, either in 3D transmon, either in JJ flux qubit, C-shunt flux qubit, fluxonium, and 0 to gamma qubit. Qubit control using quantum logic gates. Quantum logic gates are represented by unitary matrix. Quantum gates are reversible. Quantum states are typically represented by qubits from mathematical notations known as bracket. So the vector representation of a single qubit is the bracket with amplitude of column attribute and row attribute with ket 0 and ket 1. The value is represented by the ket 0, which is going to take the two value in terms of 1s and 0. The value 1 is represented by ket 1, which is again going to take the value in terms of 0 and 1. The vector representation of two qubits is going to reflect four answers. Gates for single qubit, 2 qubits and 3 qubits. Single qubit control in accordance with Bloch sphere or Bell state. Hadamard gate, Pauli's with X, Y, Z. Phase shift gates is going to reflect the same. Multiple qubit control, multi-qubit gates, 2 qubit control, swap gate, control gates, that is termed to be as a C0 gate. Frequency turning gates, cross resonance gate, 3 qubit control is Toffoli CC gate, which is termed to be as a controlled C0 gate. Fredkin is C swap gate. Cross resonance gate. Cross resonance gate is an entangling gate for fixed frequency superconducting qubits, which is implemented by applying a microwave drive to a system of two coupled qubits. The cross resonance gate was implemented in 2011. C0 gate, so-called 2 qubit entangling gate, is used here. Typical pulse duration is 200 to 500 nanosecond. Typical gate fidelities are 96 to 99%. Then next one is quantum processing unit. So this depiction is throwing conflicting requirements: long coherence, fast control and readout. Qubits, two-level systems, qubits, entangling gates, qubit readout. So ket 0, ket 1, which is single qubit control. Ket 0, ket 1, that is single qubit control. Ket 0 and control. So if combination of these single qubit control is going to be bidirectional, it is going to be present as an chain of entangling gates. It is going to throw an answer either in terms of 0 or 1 or combination of 0 and 1, or a higher composition with 0 and lower composition with 1, or higher composition with 1 lower composition with 0. This is going to be the readout. So conflicting requirements are long coherence, fast control, and readout. Qubit connections. To enable the two qubit gates between two physical qubits, resonators, also known as qubit buses, are employed to connect the nearby qubits. Transmon qubit, Joseph junction, which is gone with a physical connection. Coupling graph, energy levels. So 4 qubit bus. This is going to be 4 qubit bus. So I think we have learned the types of gates in this session, which will be more sufficient to understand what is going to be your literally your uh, ideology in terms of PCB board qubit circuitry. So thank you learners, thank you for this session.